Okay, so let's begin the basics first, and then we start getting into more complicated areas. So the first thing we're going to do is we're going to have a generator voltage VG. That's a DC voltage. It's basically going to be in a block called a converter. In the converter, we're either going to have a buck converter, a boost converter, or a buck boost converter. Now we're going to discuss each one, and we're going to generate then an output voltage, DC output voltage right here into a load resistor R, or sometimes I'll call it RL. Now the current should be DC because we want a DC voltage here. We'll just call that I out, or sometimes IDC. What controls this converter is going to be a control element, and that's going to be control, and that's going to be controlled by a duty cycle where the waveform is going to be looking like this, and this is going to be the drive into the MOSFET or bipolar that turns on and off the buck, the boost, or the buck boost converter, where we have a time t, and this is going to be always repetitive. This is a fixed frequency, and this portion is going to be the time on, and of course then this portion is going to be t minus the time on. Now we can also represent this as another one. They like to represent it as duty cycle. A duty cycle is by definition the time on over the total time t. So then you could see if we multiply both sides by t, we have dt is equal to then the time on. So therefore this portion here is dt. And then for the time off, which we're going to find as d prime time, that's going to be defined as 1 minus d. If I substitute d, I have 1 minus the t on over t. And if I multiply by t top and bottom, I have t minus t on over t. If I multiply both sides by t, I have d prime t is equal to t minus t on. And as you can see then, we can put this area here as d prime t. So now that we have all our specifications, how does this d vary? And you could see the d from this section, d equals t on over t. T on can be equal to 0, or it can be equal to t. That's your range. So therefore, for t on equal to 0, d is 0, and less than or equal to z, and this is the range of d. For t on equal to t, we got 1. So d varies from 0 to 1. What we're going to do next is we're going to then add parasitics to this. So we're going to view this as an ideal converters for the buck, the boost, the buck boost. And then later we're going to put the parasitics in. The parasitics are important because that will determine the efficiency of this system. And we want to be able to calculate the efficiency of the system. And the efficiency is going to be expressed as the power out over the power in. And we are going to show you one way to do it, the logical method of doing it. And then I'm going to show you a trick where you can do the efficiency just by sight, and it's very, very quick. We're able to get complicated systems, and we're able to get the efficiencies very quickly. That's the objective. So going back, this is the power out over the power in. Well, what's the power in? It's the power out plus the power loss. Now, that's also, if we divide by power out, top and bottom, we got 1 over 1 plus the power loss over the power out. And you know the power out, since it's a DC, it's going to be equal to V out, I out, or IDC, or it could be equal to V out squared over RL, the load, or it's going to be equal to I out squared over R, just different ways of expressing the power out. And the power loss, we're going to see that it's going to have each one of the components. There's going to be a transistor loss, there's going to be a diode loss, there's going to be a winding loss in the inductor, there's going to be core loss in the inductors or the transformers, or switching plus switching losses, and so on and so on and so on. All we have to do then is capture each one of these losses to be able to plug that into here, and we got the efficiency. So it's going to be a very convenient way of doing it. Overview again, we're going to look at what the buck is going to do. Buck, by its nature, is bucking, which is a step down feature. Now you'll see that when we develop the equation, we're not developing here. This is the introduction. The next section right away, we're going to develop all the equations. The buck circuit for an ideal, that's without parasitics, we're going to find out that the output voltage over the input voltage is going to be D. So that the output voltage then is going to be D times the input voltage. Since the D varies between 0 and 1, you could see that the output voltage is always going to be less than or equal to the input voltage. Now, when we do the parasitics and add all the parasitics into the circuit, that's the winding resistance of the inductor, the RDS(on) of the transistor, of the FET or transistor, the switching losses, and any other losses, the Zener diode losses or the synchronous rectifier losses. We add all those losses. Those are called parasitics. Then we're going to find out the output of the input voltage is the same, except it's the efficiency times D. And therefore, then the output voltage is going to be equal to the efficiency times D times V sub G. This is going to be the buck circuit. Now we're going to then deal with the boost circuit, because sometimes we don't want to step down the input voltage. Maybe we want to step up the input voltage for higher voltage. Then what we're going to find out is the ideal transfer ratio between output and input is going to be V out over V in, and that's going to be 1 over D prime. As you remember, D prime is 1 over 1 minus D. Now you could see that then the output voltage is going to be 1 over 1 minus D, which again 1 over D prime, times V sub G. Now when we look at this, since D is at the range of 0 less than or equal to D less than or equal to 1, then this 1 over is always greater than or equal to 1. Therefore, then, the output voltage is going to be greater or equal to the input voltage. The parasitics, when we add the parasitics to it, then what we'll have is the output over the input voltage is similar efficiency over 1 over D prime. Now, the last feature is going to be the buck boost. And in the buck boost, just like the name implies, it steps up or steps down the converter. Now, this could be used as battery charges, as you may want the output voltage at 3.3, but the input voltage goes, say, 1.5 to 10 volts. So that you want to keep 3.3, so therefore at sometimes the input voltage may be at 1.5 volts, so you want to step that up to 3.3 volts or 3 volts on the output, or the input voltage may be at 10 volts, which means that we have to step it down to again 3 or 3.3 volts. So that's when we use the buck boost. So the ideal ratio again will be equal to V out over VG, and we'll wind up with D over D prime. If you really look at that, that's D, which is the buck mode, times 1 over D prime, which is the boost mode, and hence the name buck boost. So you could see that the output voltage now is going to be D over D prime times the input voltage. And since, again, D varies from 0 less than equal to D less than equal 1, you can see at 50%, then the output voltage will equal to the input voltage, because D will be 0.5 and then D prime is 1 minus D, which as we go on one side of the D or the other side, will either step down or step up. So now the last one we add is parasitics. With parasitics, we have the output over the input voltage. That's going to be just efficiency, D over D prime. So this is where we're going, and of course then your output is going to be equal to the efficiency, D over D prime, times your input voltage. And we could see again, we could step down or step up to the converter, and that's what I mean going back into the control of this. Depending upon what this converter is, we just call a general converter, and we could see this control element is the D control, the duty cycle. Now I will use V out or V interchangeably. A lot of times I'll use V, and so you don't get mixed up, and this is VG, meaning the generator voltage. So this is where we're going, this is where we're going to head, and we're going to start the first section with an ideal buck converter.